Hello everyone! Today we'll talk about the solution to the problem redundant connection. While for me and probably many others, by just reading the title we immediately know that this redundant connection is simply an edge that lies on a cycle in a graph, there is a bit of a red herring with this description that we're given, and there is also a twist in this problem that will make some solutions better than others, because we have to return the answer that occurs last in the input, where the input is a list of edges. So this red herring that I mentioned is that there is a tree, and of course in a tree there is no redundant connection, and then an edge is added. That edge creates a cycle, and so this is of course a redundant connection. You can remove it and it's still a tree. Nothing breaks apart into more than one component. But the red herring is that really any edge that lies on a cycle is a redundant connection. That's essentially a definition of a cycle, because when you have a cycle, then that means that from every node to any other node, you can get in two ways. Along one part of the cycle or the other part of the cycle. In a sense, going right at the beginning or going left at the beginning. Which means that we just have to return the last edge in the list of edges that lies on some cycle in this whole graph. And that means that some ways of calculating it are easier than others. I think a DFS, for instance, would be harder than usual because of this requirement of returning the last occurrence. But a disjoint set union, so a union find data structure, is very nice here. Because really the solution is just to initialize our disjoint set union, go through all the edges, union the two edges, the two ends of the edge, and if those two ends were in the same component already, then that means that this edge lies on a cycle, and so we just update the result to be equal to that. So we'll be updating the result with new edges all the time, so the last edge which lies on a cycle will be the last edge which updates the result, so we can just return the result. So this is the shortest way of doing it. And if you're familiar with the implementation of a DSU, then this is the whole solution. If not, let's go quickly through this implementation. I recommend as an internal data structure to hold a list which is POS, so it's parent or size. If this is negative, then this is minus size of the component. This is for path compression and for smart joining. If it's positive, or 0 or positive, it's the number of the parent. So now our find, we check. If it's less than 0, this POS, that means that we are our own parent, we just return ourselves. Otherwise, we have a parent. So we call find on our parent. This becomes our parent, so this is path compression, we return this parent. And now to union, and we'll be returning false if they were already unioned, true if they were indeed in separate components. We find the representative for both, so we just call F. They are equal, they were in the same component, return false. Otherwise we have to join them, and to join them correctly, so smaller to larger, we can use our parent or size to check which is larger. So because we'll be connecting V, the father of V, or the find of V with the find of U, we have to of course add back the size of one to the other, and here we just swap their order if their order is incorrect. So if the size of FU, here we have greater than, but this means that this is a greater than negative value, which means that this is a value that's smaller with respect to the absolute value. And we want to get the smaller to larger, and we want to connect up to FU, so FU has to be larger.